Hello, my name is Øystein, and this lecture is on statistical inference. There is also a lecture on basic concepts in statistics available, so you might want to check that one out as well. But like I said, this lecture is about statistical inference. Before I get to tests and confidence intervals and that stuff, I want to talk about the normal distribution and the central limit theorem. I'll also discuss false positives and negatives and power. The normal distribution is also known as the bell curve or the Gaussian distribution, and it has two parameters, the mean and the standard deviation. In this picture, the black curve has mean equal to 0 and standard deviation equal to 1. This particular version of the normal distribution is called standard normal. So mean 0 and standard deviation 1. The orange curve also has a mean at 0, but the standard deviation is 0.4 instead of 1. As you can see, that means that more of the mass is close to 0. The purple curve is the same as the black, but the mean is shifted to 1. The normal distribution is very important in statistics for several reasons, and one is that measurement errors tend to be normally distributed. Okay, so the formula of the normal distribution looks like this. It's not important to memorize the formula, but if you're going to work with statistics, I think you should have at least seen it. Mu is the mean or expected value, and sigma is the standard deviation. If we remember the last figure, mu is where the plots reached their maximums. A standard deviation of sigma means that about 68% of the sample is going to be a distance of sigma or less from the mean, and about 95% of the sample is going to be a distance of 2 times sigma or less from the mean. This x tilde n mu sigma squared is read. X is normally distributed with mean equal to mu and variance equal to sigma squared. The central limit theorem states that the mean of a sample is normally distributed when we consider many observations. Here it's written more formally. In this case, the x with a bar is the average or mean of a sample. The underlying distribution of x can be anything. It could be uniform or normal or Poisson or any other distribution. If we have enough observations in the sample, the mean is going to be normally distributed. The formula says that the sample mean minus the true population mean divided by the standard error of the sample is normally distributed with mean 0 and standard deviation 1. And like mentioned, this is called the standard normal distribution. Let's consider an example with duration of pregnancy. The mean duration of a pregnancy is about 40 weeks, but the range is about 26 to 43 weeks. So in other words, one may give birth 3 weeks after the due date, but 14 weeks before. This is not symmetric, so we see that pregnancy duration is not normally distributed. Now say that 30 children are born each day in Bergen, for example. These numbers are the durations of their pregnancy. So 27, 30, 30, 30, and so on are the durations of their pregnancies. The figure shows the density plot. So most are born around 40 weeks, but some are very premature. So one was born at 27 weeks and 3 were born at 30 weeks. So very premature. If we focus on each bed, we see that the first bed is occupied by a baby born at 27 weeks, and the last bed is occupied by a baby born at 43 weeks. Now let's see what happens if we consider more than one day. In this example, we consider all children born in 1 week. We assume that they are moved after the first day. So this means that each of the 30 beds has had 7 children in it. If we take the mean of the pregnancy duration of the children staying in each bed, we get the numbers below the figure. We see from the figure that the means look more symmetric than the single observations did, right? So when we have the mean of 7 observations and we plot the density plot, then it's more symmetric than when we only considered each observation or one observation instead of 7 observations. We also see that no beds had a mean of less than 36.9 weeks. This is because it's very unlikely that all the children sleeping in one bed are born very early or very late. So a mean of 27 would mean that all the children who used that bed, all the 7 children who used that bed, would have had to be born around week 27. Still, the density plot does not look like a standard bell curve, right? Now, next, we consider all children born in a month. So we have 30 children in each of the 30 beds. The density plot looks more like a bell curve, but we're not quite there yet. And remember, each number is a mean of 30 pregnancy durations. Okay, if we expand the period to 100 days, we get these numbers and this figure. This looks very smooth, symmetric, and nice. And once again, each of the numbers represent the mean pregnancy duration of 100 babies. So this is what the central limit theorem is about. When we have a lot of observations in a sample, the mean of that sample will be normally distributed. In our case, we have 30 samples with 100 babies in each. And when we plot the density, we see that it looks like the bell curve. In the other cases, when we had fewer observations in each sample, the density plot looked less like a bell curve. Okay, now we move on to testing. This is a table of the sexes of children born on one specific day in Bergen. As usual, there are 30 children born each day. Now we want to know if the probability of having a girl or a boy is 50% each, or if one sex is more likely than the other. So how do we go about figuring that out? The table suggests that having a girl is more likely. Now, this is not a very solid finding, but why? And the answer is that we have too few observations, right? Adding more children turns the distribution upside down. And now it seems like boys are most common. But how do we know if this is true? Adding even more children, we see that the proportion doesn't vary much. It's between 47.6 and 48.6% when we have 300 or more children. Still, how can we know if the probability of having a girl is the same as the probability of having a boy? And to answer this question, we may perform one or more statistical tests. Such a test has a null hypothesis, H null, which is assumed to be true. And note that when I say assume, it doesn't mean that we actually think that it's true. It means that the mathematical model that we build will be based on the null hypothesis. So the mathematics will sort of come from the null hypothesis. And H null is normally that there is no effect or no difference. In our case, this means that the probability of having a girl is 50%. So H null, probability of having a girl, is 50%. Of course, it's also the same for the boys. There also has to be an alternative hypothesis, and this is often called HA or H1. And the alternative hypothesis should be the opposite of the null hypothesis. Because we assume that the null hypothesis is true, we can calculate the probability of observing the data that we have indeed observed. So the probability of observing the data that we have observed. In the first case, the probability of interest is the following. What is the probability of having either 17 or more girls or 17 or more boys if the probability of having a girl is 50%? And it turns out that this probability is 0.58 or 58%. This means that observing at least 17 boys or at least 17 girls in a sample of 30 babies happens quite often if the probability of having a girl is the same as the probability of having a boy. Actually, it happens more often than not. So 17 is not a very big number in this situation. We can do the same for the other situations, and we get these probabilities. Focusing on the bottom row first, we see that the probability of observing 48.6% or fewer girls in a sample of 300,000 is almost zero under H0. This includes the probability of observing 48.6% or fewer boys. So if the probability is 50% of having a girl, we would almost certainly have more than 48.6% girls in our sample. That's very strong evidence against H0. In other words, we can confidently reject H0 and say that the probability of having a girl is not 50%. The same applies to the fourth row. As mentioned, the top row provides no such evidence against H0. And this is true for the second row as well. But the third row is more interesting. Now, given that H0 is true, there's a 1% chance of having fewer than 48.4% girls or fewer than 48.4% boys in the sample. Now, is this evidence against H0? In many cases, we say yes. A test with a p-value less than 5% provides significant evidence against H0. This 5% limit is called the significance level. And the significance level may vary from situation to situation, but 5% is pretty standard. Now, what if we want to know what the probability of having a girl is? Rejecting H0 only tells us that it's not 50%. Based on the tests, we can't even be sure if it's more than 50% or less than 50%, although the data would seem to suggest somewhere around 48%, right? So what do? We need some kind of error measurement that gives a large error when we have few observations that vary a lot, and a small error when we have many observations that vary little. This is exactly what the standard error does. Right? Remember? And it turns out that adding and subtracting 1.96 times the standard error from the estimate gives you a very nice error interval. And this is called a 95% confidence interval. The interpretation of a 95% confidence interval is a bit complicated, but roughly we can say that we expect 95% confidence intervals to cover the true value that we're trying to estimate 95% of the time. In the bottom row, this would mean that the true probability of having a girl is probably not far away from 48.6 because the confidence interval is quite narrow, right? 48.4 to 48.8. Note that the confidence intervals in the two top rows contain 50%, and these were the two rows where we could not reject H0. Also note that the number 1.96 that you are supposed to multiply the standard error with only applies when we have enough data. So the construction of a confidence interval in this way is based on the central limit theorem. So we should have at least 30 observations, but that's not a problem in our case. If we have fewer observations than that, we need to use a larger number than 1.96. However, this is not supposed to be a mathematical lecture, and most, I would say all, statistical programs have methods to calculate confidence intervals. There are several tests to use when doing data analysis, but the most common are the chi-square test for proportions and the t-test for continuous data like height and weight. We will not go into detail about how these tests work because you will probably use computer programs to obtain your p-values and confidence intervals anyway. But again, when we test for proportions, the chi-square test is normally the best. And when we test for continuous outcomes, we normally use the t-test. A significance level of 5% gives a 5% chance of rejecting H null, even if H null was true, right? By definition. In the example with the boys and girls, this means that even if the probability of having a girl was 50%, we would still reject H null 5% of the time. And this kind of error is called a false positive or type 1 error. False negatives or type 2 errors occur when we do not reject H null, even if H null was false, while the type 1 error rate only depends on the significance level. The type 2 error rate also depends on the number of observations. For example, we did not reject H null when we only had 30 or 300 babies, but when we had 3,000 babies or more, we rejected every time. However, if we had chosen a different significance level, for example, 0.5% and not 5%, we would not have rejected H null when n was 3000, right? Because the p-value was 0.01. Statistical power is the probability of rejecting H null if H null is false. In this table, the power is equal to 1 minus beta. Note that the significance level is alpha. So if H null is true and alpha is 5%, we keep H null 95% of the time and reject it 5% of the time. If H null is false, the false negative rate is beta, right? So as mentioned, this depends on both alpha and n, but also the distribution of the data and the effect size. Going back to this table again, we see that the power was very low for the first two rows. And now remember that even if H null is true, we reject 5% of the time. So a power of 5% is a minimum. And having 5.3% is basically the same as having no power. In the third row, we got a pretty low p-value, but the power was only 35.2%. So this means that we essentially got lucky. About 2/3 of the time, we would have been expected to keep H null, which would have been wrong, right? But sometimes you're lucky. The bottom two rows reject H null more or less every time. Now, if we are going to conduct an experiment or spend time doing analysis, we should always first consider if we have enough power, if it's worthwhile. Okay, so that's it for this lecture on statistical inference. I hope you enjoyed it. Thank you very much.